I'm going to stop my video and hopefully everybody can hear me, I hope. Okay, I'm going to stop my video. So I'd like to welcome everybody to the California APCO, the virtual vendor expo. Kind of missed the live events that should have been held up in Northern California for NAPCO and CPRA down in Southern California. But hopefully next year we'll get together and we can talk face to face and you can touch some of our products. But what I wanted to talk about today, this morning, as one of the first presenters of this day one in the first morning, I want to talk about some of the fundamentals of analog receiver voters. And interestingly enough, there are still a lot of radio systems out there relying on voters of this type, analog receiver voters, specifically FM conventional. We're not going to talk about digital voting. Digital voting is a completely different animal. Digital voting, we rely on bit error rate, and it's very difficult sometimes to vote digital communications because of the presence of vocoders and what the vocoders do to the voted audio, the received audio. And in terms of what analog voters rely on is noise, and noise is very important to analog receivers. So I want to really start off very basic. I want to talk about radio coverage, and especially the reason we deploy voters or comparators is to support larger coverage areas. So I want to start off talking about very simple communications and simplex communications, which is still important today, which is still relied upon primarily by fire services that are operating in the fire grounds or supporting maybe an incident in a building. And simplex communications is quite simple, meaning the transceiver or the radio will transmit and receive at the same frequencies. And you can see in my diagram, I have the transmit and receive frequencies, not discrete frequencies, but I'm going to use a designation. And in this example, F1 is the transmit and receive frequency. So this means I can deploy what you may have heard this term, non-supported simplex. The non-supported part of that phrase means that we're not going to rely on infrastructure to support our communications. We're going to rely on the ability to transmit from one subscriber unit directly to another subscriber unit without relying on any outside influences or infrastructure. So this is important for fire grounds, as I mentioned earlier, because we, in many cases, do not want to deal with the infrastructure. We want somewhat reliable communications on the fire grounds, and we want to reduce interference. So simplex communications or non-supported simplex is still very viable and is commonly used. But one of the issues we see commonly with non-supported simplex is the transmit power of the subscriber units, as well as the sensitivity of the receivers. And if I'm not able to transmit with the sufficient enough power, some subscriber units that are lacking in receiver sensitivity will not be able to receive that information, and we lose communications. And one of the best ways to remedy this issue of coverage is by adding a radio relay of some sort. We commonly call those repeaters, and this is duplex communication at its best. And if we look at the transmit and receive frequency designations that I have, particularly for one of the patrol vehicles on the left, I transmit it at frequency F2, and my relay or my repeater site has a receiver that will receive that transmission with frequency F2. We can then, at the repeater or relay site, retransmit at a completely different frequency. And if you'll notice, my partner in the other vehicle, the receive frequency is R1. So this is duplex communications. The term duo means two. And so I now have two communication paths. One is a transmit path, which in this case is F2, and I have a receive path, which is F1. And sometimes we'll understand that when we look at our subscriber units, and they will have an offset, a transmit receive offset. And this is the duplex frequencies, or the separate transmit and receive paths. And this then allows us to increase our coverage area by adding these relays. But that doesn't really tell the whole story. So now the receiver sites, the remote receiver sites, will now support our subscriber units with low transmit power, but there's always a physical coverage with respect to the transmitter at the relay site. So if I'm out of coverage, naturally I am not, as a subscriber unit, going to be able to receive that communication again based upon the lack of transmit power at my relay site and the receiver sensitivity of my subscriber unit. We can then fortify the coverage area by adding more repeaters or relay sites or receiver sites, and then taking that information and consolidating that information at a call center or a dispatch center. And this allows subscriber units to roam throughout an entire region, hopefully being within earshot of a receiver site. I can take that receive audio, bring it into a location of consolidation, and then I can take that information and deliver it to a transmitter. You can see the upper left, I have a site that includes not only a receiver, but also a transmitter. And this is a single transmitter that's covering a very large region. So we'll talk about architecture here in a moment, but this is a very typical system that relies on many distributed or satellite receiver sites. And the way we deal with the receive audio, particularly I have 5 sites here, I might be in an overlap situation where my subscriber unit is that transmission is being received by multiple receiver sites. I can take that receive audio and I can deliver it to what we call a comparator. And the comparator is a piece of hardware that will do exactly as it describes. It will compare the quality of receive audio from my multiple or distributed receiver sites, and then select a single receiver site with the best quality audio, not the loudest audio, but the audio of the highest quality, meaning less noise, right? So that's really the purpose of a comparator or voter, is to allow multiple receiver sites to be distributed, fortifying my coverage area, but also having the ability to select only one site based upon audio quality, not based upon amplitude, but based on the quality of the audio. All right. So how do we make that assessment? And so there's many ways of making that assessment in digital communications. We'll use bit error rate, for instance, but we're talking about FM conventional communications. And there's a couple ways we can do this. And one of the most common ways in FM receivers is to just measure the noise. So I've got a very simple system here with 3 satellite receiver sites, terrestrial sites, that are feeding the receive audio into a voter or a comparator, where each of the sites are continually being assessed for quality. And I'm going to move my transmitter, which is a subscriber unit, away from one of my receive sites. And you can see the dotted line around my coverage area. And we're going to be able to listen to not only the audio being received from the receiver, but we're also going to listen to the noise that receiver is generating. And remember, the voter, its bread and butter is noise. We want to hear noise at the voter or the comparator, because that's how we determine quality. So I'm going to let you hear this audio. I'm going to stop talking, but let's watch the little graph develop on the bottom, and I'm going to watch the transmitting subscriber unit move away from the receiver site.
323 to 584. T5. Adam Young, 1955. Okay. 3 we're at 10 to Graham, waiting for a tow. I believe it was called on channel 1. Okay, we have 42 coming out there for the head.
Okay, kind of interesting. You know, we've have a graph here that depicts the audio being received at my remote receiver site, and we see the audio in green, in the green line, and you might notice that it's at a steady state in terms of amplitude. If we look at the noise in the graph and below, As we create margin between the transmitter and the receiver site, we can see the noise start, or we can hear and even see the noise start to increase as we create margin. And if you look at the green line to the right, you can see it drop away. And we call that the capture effect. And so really the way I kind of equate or kind of help describe the capture effect is maybe if I'm driving my car up a mountain, up a mountain pass, and I'm listening to an FM radio station or radio station playing music, as I start approaching a pass and maybe even crest the pass, I'm creating margin with that radio, the FM radio station. And something you'll want to observe when you're listening to this audio as you pass over the mountain pass is that the audio, for the most part, stays constant. The amplitude stays constant until I crest the pass, and the audio drops away immediately. And we call that the capture effect. And we'll talk about capture and capture ratio and non-capture region a little bit later once we start talking about simulcast. But for the most part, the nice thing about FM communications is we're modulating and demodulating the system with respect to the instantaneous frequency of the carrier. And we take that information and we're going to send it through a super heterodyne receiver, and we're going to deconvolute that information and extract the baseband analog audio, which is going to be our speech or music coming from a radio station. But as I create margin, you'll notice that the noise increases. And this is how we, in some cases, we'll analyze the quality of the receive audio based on the spectral noise. So in FM communications, the correlated audio stays the same, but the noise increases as I create margin. So I'm driving over that pass. Not only does the audio still sound good, but the noise starts increasing when I listen to the audio in my car. So how does the noise change? And a lot of that has to do with the receiver. And this is a little block diagram of the remote receiver on the mountaintop or on the top of the building, for instance. On the left, I have my subscriber unit, my handheld. It could be of a mobile and vehicle, transmitting a carrier that's frequency modulated. And at the right is my baseband audio. I can have a speaker there so I can listen to the audio, but I have a comparator and a voter. And so this is one of my remote receiver sites. So on the left-hand side, my subscriber unit transmits. I send a carrier signal over free space that's been modulated. And once it arrives at the heterodyne receiver, I start going through some stages. I go through my first LO. I convert that information into an intermediate frequency, and then I deliver it through my limiter, my discriminator, which is really the demodulating function that takes the FM information, the frequency modulated information, and turns that into a baseband signal. Again, we deliver it to a speaker, or in this case, a voter. And this is what you and I hear as a human emerging from my remote receiver. So how do we deal with the noise, or why do we have noise? And one of the nice things about FM conventional communication is, for the most part, if I have a really nice fully quieted signal coming in from my left-hand side, my subscriber unit, that discriminator will be able to detect the instantaneous frequency delivered from that carrier and turn that into audible energy or information that you and I can hear. So that's one of the nice properties of FM is we key on the FM information coming from the subscriber unit. We don't really care about the amplitude, but we do. I'll show you why. But in AM communications, the amplitude of the carrier is very important. That's really the information. In FM conventional, it's all about the instantaneous frequency that's been driven down by the local oscillator here in my receiver. So what dictates the noise? You know, we heard noise when I created margin in my previous example of that subscriber unit moving from one region to another. And this is basically the responsibility of the limiter in the receiver. And the job of the limiter is to remove some of the amplitude noise. So if I look at my subscriber unit on the left, it's propagating a signal over free space. A lot of things can happen between that subscriber unit and my receiver site, and that could be mechanical interference. EMI, RF interferers, that could perturb the amplitude of the signal. But remember, this is FM conventional communications. We're interested in the frequency content within that carrier. But as that signal travels from my subscriber unit through free space, I'm beginning to perturb the amplitude. And so the job of the limiter is to essentially strip off the variations in amplitude, which we call noise. So any instantaneous changes in amplitude right there at these little peaks equates to the noise that we hear. All right. So if we apply a limiter, we can, for the most part, strip off that amplitude and create a nice constant envelope where just the FM information is delivered to the discriminator and our audio is very clean. So that's one of the great attributes of FM communications with a fully quieted receiver, is that the baseband audio is going to be essentially free of noise. All right, so let's create margin. We saw my subscriber unit moving away from my receiver site. And if I deliver a weak signal that is not fully quieted in receiver or is below 12 dB SINAD, now the limiter no longer has the dynamic range, to reform the amplitude envelope or create a constant envelope. And now the amplitude noise then begins leaking into the discriminator. And this is the noise we hear, right? We create margin, the carrier becomes weak, the limiter is unable to reform the envelope, the amplitude envelope, the noise leaks into the discriminator, and that's what we hear. So when we create margin, that's why, because there's not enough dynamic range in the limiter, the FM limiter, to strip out that amplitude noise. All right, so there's other algorithms that receiver voters and comparators will use, and this is primarily for AM communications, amplitude modulation, where the envelope is where our voice energy or information resides, as opposed to in FM communications, it's the instantaneous frequency within that carrier. So I've got another graph here. I've got an aircraft, and in air traffic control, AM communications is the primary means of communications between aircraft and ground. And the reason being is because in FM communications or digital communications, those types of communications has a suppression, a means of suppressing other signals, particularly in FM communications. Again, when I use my example of driving my car over a mountain pass, I might be receiving a FM signal radio station on one side of the pass, and once I begin cresting the pass, I now then lock onto another station on the other side of the pass. I'll suppress one and lock onto another. So that's one of the other nice attributes of digital communications or FM communications, is its ability to suppress a lower power signal and grab on or latch onto or capture a strong signal. So in AM, it's a little different. AM, and this is a safety concern for aircraft, is AM will consume all AM signals. And so we can have 2 aircraft, 3 aircraft, 4 aircraft, even the ground speaking, and we can hear the communications. And this is for safety purposes. If the aircraft has an emergency situation, they can announce that emergency situation or information over the radio system, and everybody will be heard. And so voters have to handle that type of communications a little bit differently, because there's no capture effect or suppression of weaker signals. So let's listen to the audio.
542, turn 10 degrees left, please.
10 left, solution 542.
Solution 542, turn right heading 340.
340 heading, solution 542.
Eagle 3655, turn right heading 250, descend and maintain 2000.
Heading 250, descend to 2000, 3655. Tower 120.95.
Okay, so I guess hopefully you heard some of that, and you can hear the audio fading away, the pilot's audio fading away, whereas in the FM conventional explanation, you notice that the audio amplitude remained constant throughout. Then we hit the capture and we lost the audio instantaneous. In aircraft for amplitude modulated communications, the audio fades away. As long as we got something coming into air traffic control, we can hear that aircraft. So it's kind of a safety concern. That's why we primarily use AM communications in aircraft and not digital communications. The ATC communities for many years has been trying to transition to a digital communication system, but I don't know if that's ever going to happen soon, because the entire air traffic control community has to transition to digital communications. So maybe in our lifetime we might see that, but I doubt it. So this is interesting because you notice that the noise stays constant even by margin, because the noise is actually thermal noise generated at the receiver site, and that never changes. Whereas on the FM example, you notice the noise increase as we created margin, and that's because of the FM limiter. So in this situation, we use signal to noise ratio. And so this is, again, a different way of assessing the quality of audio coming from one receiver site only. We might be able to hear the aircraft on all my receiver sites, but there's always going to be one site that has, in this case, better signal to noise ratio or lower spectral noise, and we're going to vote that site and retransmit it or deliver that information to the dispatcher. All right. So again, in FM communications, we only key or focus our efforts based upon the spectral noise above a certain threshold, and that's typically above 2 kilohertz. In AM, we have to look at not only the correlated speech at the lower region of the spectrum, but also the spectral noise. So it's harder for us to use digital signal processors in AM communications. It's actually more difficult. FM is very simple. We just use digital filters to measure spectral noise above 2 kilohertz, and that simplifies our efforts. Okay, so that's how we measure quality. Not how loud a system is, but based upon the quality. So let's talk about some architecture. There's just a handful of architectural variances that we see in voted systems. And this is one of the most basic systems where I have multiple receiver sites and a single transmitter. And as I roam throughout my region, you notice my transmitter on my subscriber units transmitting a -1 or a -1, and my receivers are all at -1. So this means, as a user of my subscriber unit, I have a really nice handoff. I don't have to change channels. I can just roam throughout my operational area, and I will be hopefully within coverage of a receiver site. One of those sites, I could be transmitting, and all those sites could be receiving my information from my subscriber unit, but there's always going to be one site that has the best spectral noise or very good signal noise ratio or a great signal to noise ratio. And I deliver that information to the voter or the comparator, and I have the opportunity to deliver that to either the dispatch console, or I can send that to in this case, a single transmitter. You notice the frequency is F2, meaning I have duplex communication. I receive on F2 and I transmit at a different frequency. So I have a very large relay system with one transmitter. This is very spectrally efficient, and I have a single transmitter. So this is a good example of a system that I would deploy that has no coverage issues. I might deploy this in Nebraska, where I don't have issues such as mountains or buildings that might perturb my transmission from my subscriber units. Some of the disadvantages we see with a system such as this, particularly a single transmitter, is you have a single transmitter. So if I attempt to maybe install this type of a system in the Rockies, for instance, I'm going to have some issues, particularly on the transmit side, because a single transmitter might not be able to overcome some of the geographical constraints of a mountainous region. So this is still a very common system, single transmitter, multiple receiver sites. Another architectural variant of a voted system is what we call a multicast system. And you might notice that my single large transmitter is no longer present here in the middle, but now each of my remote receiver sites is also supported by a transmitter. Right? So we're co-locating the transmitter and receiver at my different sites, receiver sites, but I still am employing a voter or a comparator to assess the quality of the received audio. And so what do I gain from a system like this? I can now deploy this system in the Rockies because now I have transmitters that have almost equal coverage as my receive coverage. And so this allows me to better distribute my transmit audio that is voted from one site. Remember, I vote from one receiver and I transmit, in this case, out all of my transmitter sites. All right. So some of you that are thinking ahead of me, you might be thinking, oh, this could be a problem because, once we start talking about transmitting multiple signals into the environment, we run into issues that can cause phase degradation, especially if I'm operating in a overlap region where I might be able to receive both transmit signals from these these remote sites, and that will create interference in my subscriber unit. So the advantages of a system such as this, obviously, is the transmit coverage is fortified because I have transmitters now throughout my coverage area. I do not require expensive simulcast equipment, which I'll talk about here in a moment. But so this is still a very viable system for public safety, fire services, commercial, retail. It is nice because now I have the ability to transmit over large distances without having a very powerful transmitter. But some of the disadvantages can be costly, and because we're now spectrally inefficient, meaning my transmitters now all have to have a different transmit frequency. They can receive at the same frequency, but now all my sites have different transmitters. The handoff or the user experience is not that great. I have to, when I go to a different region, I have to change my channel. If I go to another region, I'll have to change my channel on my subscriber unit. So the handoff is not that great, but maybe I need better transmit coverage. So this is still a viable system. There's lots of multicast systems out there, and the licensing of the transmit frequencies then can be an issue because this is now a spectrally inefficient system, right, with multiple transmitters, which again will cost me some money. The other system, which I like calling this kind of the pinnacle of radio systems in terms of coverage, and this is a simulcast system. And if you look at the diagram, it looks very similar to the previous multicast configuration. I still have receiver sites. I also have transmitters at all those receiver sites. So what this tells me, I got good transmit coverage. But what's interesting about simulcast is if you look at the frequencies of my subscriber unit, I transmit at a -2 and I receive at -2, meaning all my receiver sites receive at -2. All right. My subscriber units receive at -1. And interestingly enough, my transmitters all transmit at the same frequency, a -1. With the previous example of multicast, all my transmitters had to be different. And as I mentioned earlier, if we have a system such as this, which is a simulcast system transmitting all at the same frequencies, there might be a chance that we might be interfering with the signal. We might have some phase degradation due to the similarities of the transmitted frequencies from the transmit of the remote site. So it's very spectrally efficient. I'm now transmitting with one frequency. I have great transmit coverage, but the issues that are quite evident in a simulcast system is how do I launch the transmit information into the environment? And this requires costly equipment and the ability to time the transmit information out into the field, right? So the reason we need to time that is some of my my description of my car driving over a mountain pass. Once I reach the mountain pass, I might be receiving radio station communications, music on one side, talk radio on the other, at the top of my pass, and that's because I am in what we call the non-capture region. FM receivers have what we call a capture ratio. And one thing I mentioned earlier about the nice thing about FM communications is if I create margin Or for instance, if I move my receiver closer to one transmitter, my receiver in my handheld will now begin to favor or capture or lock into, in this case, transmitter A, and suppress information coming from transmitter B. And this all depends on not only the capture ratio of this radio, but how am I physically positioned in the overlap region. And when we design a radio system, we have to apply engineering. We just don't deploy transmitters and receivers in my operational area just because I can do that. We need to use thoughtful engineering and make sure that the coverage is adequate. And in a system like this, the coverage in terms of overlap is not too much. You always need overlap. So if I reduce the power of these transmitters, I might reduce that non-capture of the overlap position, but there's also a chance that there will be no coverage. So there has to always be some overlap. And so if we look at some of the specifications of a subscriber unit, one of those is the capture ratio. And the capture ratio is really defined as how many dB of signal coming from a transmitter A or transmitter B in this situation, how much more power should be coming from one transmitter with respect to the other transmitter to suppress that low power transmitter. And we equate that to the capture ratio, and we express that in decibels or dB. So for instance, if transmitter B, its signal, its effective radiated power was 20 dB lower than transmitter A, we're now going to try to favor transmitter A because it has a little bit more power, and we're going to completely suppress B. And because of the capture effect, we're going to hear nothing coming from B. All right. So once we're in this overlap region, now the capture ratio comes into effect. If I have 10 dB of a capture ratio, and there is no 10 dB of difference between transmitter A and transmitter B, right? If I'm right here in the middle, there's probably 1 dB of difference. My subscriber unit will not be able to suppress one of the other side. I'm going to receive communications from both sides. It might be good, it might be bad. So the launching of the communications, the transmitted information, has to be simultaneously and in phase, such that we don't create interference. So I have audio that we're going to hear in a moment, but these are some of the terms you're going to hear when you talk about a simulcast system not functioning properly, particularly in the non-capture region. Sometimes we call this carrier to interference ratio for us. For some of the radar folks out there, we might call that co-channel interference. It's really all the same thing. We want to suppress the other signal and capture or focus on another signal. So these are some of the terms you're going to be hearing, as well as group delay, phase, differential amplitude, and the such. And the way we mitigate this is by controlling the launch of the transmit coming out of these transmitters such that they're arriving in the non-capture region at the same time. It's not trivial. It's very difficult to do, requires GPS, rubidium time sources, external timing references. We're talking in terms of alignment. You're looking at microseconds. All right, so this very precise alignments have to take place in terms of launching the transmit information into this non-capture area. So hardware is a great way of mitigating, but also shaping the coverage and using engineering practices to make sure your coverage area is overlapping, but not overlapping too much. So I've got audio I want you to hear. This is degraded audio, and you're going to hear a tunneling effect and kind of a whining effect. And that's the two transmitters trying to beat on each other, trying to interfere with each other because the phase of that information launched from those two transmitters is not the same.
934, Highway 33 in Howell on a warrant. 43, 41. Looking for the engine. 10 for 6642, level 28. Down you look up on Mike Papa, 74 Delta.
Okay, so I guess you get the idea. The audio is legible, but it can be kind of disturbing because of the whining or the ringing sound. And if the phase is correct, meaning or incorrect, greatly incorrect by 180 degrees with respect to each other, you can even cancel out the audio. So the launch of that transmit audio is very important in a simulcast system. This is still the pinnacle of a coverage type of situation using multiple receiver sites, but it's not trivial. You have to use expensive equipment to make sure that the non-capture region, the effects of the phase degradation is kept to a minimum, right? So one of the last system I want to talk about is a Simplex system. Remember, our first discussion was talking about unsupported or non-supported Simplex, where we don't use infrastructure. We just talk handheld radio to handheld radio, car to car, because we transmit at the same frequency. There are Simplex systems that use receiver sites, and they're primarily used by fire protection districts that have a area of responsibility that might be a national forest, BLM land, where they need radio coverage, where they can send communications back to a dispatch center. And in this situation, the voter or comparator acts kind of in an interesting fashion. But if I look at the transmit frequencies, I'm at a -1, I receive at a -1, and all my receivers receive at a -1, which is good. This means I have a nice handoff. I can roam throughout my area of operation without having to change my channels. But one interesting thing here in a Simplex situation is my transmitters also transmit at a -1, meaning if my transmitter transmits, these receivers are eligible to receive that information. And as you can well imagine, if I transmit out my transmitter and deliver that to my receiver, that audio is going to go back into the comparator and the dispatch console, obviously, and I'm going to create a side tone and a feedback, and the system will not function properly. So in a Simplex type of architecture, the subscriber unit, when it's in a transmit, in a transmit state, the voter will not repeat audio, right? Will not repeat that audio out the system-wide transmitter or transmitters. It'll deliver only to the dispatch console, right? So we negate the voting process. We still look for the site of best audio quality, but we take that information and deliver it to the dispatch position only. We do not send it to the transmitter, right? Because we can receive that information and we're going to create feedback. Conversely, when the dispatch operator wants to transmit out to the system or reply to the operators in the field, the voting is terminated, right? So we can send that information to the transmitter or transmitters, but we negate the functionality of the receivers. We can still receive. We bring the audio to the comparator, but we don't do anything with that information because we do not want to retransmit or rebroadcast any information from the field and create, again, that side tone or feedback. So these are still popular systems. Again, I see most of this type of architecture in a firegrounds, not a firegrounds, but a fire protection system or environment where firefighters, for instance, rely on Simplex communications or unsupported Simplex. Transmitter steering is still a viable function where the dispatch console can use very many methods to direct their communications only to a single transmitter. So this works great in a multicast situation as well, but we have many means of signaling from the dispatch console to tell the comparator or voter, hey, I want to go to a specific transmitter. We call that transmitter steering. We can use telnet, serial control. We can even emit function tones from the dispatch console to tell the voter or comparator to say, hey, I want you to send my dispatch information, my audio, to a specific site so I can speak into a specific region. Right? So steering is still, manual steering is still very popular out there. There are automatic methods of steering. And so intuitively, the voter or the comparator in this case will understand when a region has a receiver that's fully quieted, they'll deliver that high quality information to the voter. The voter will remember where that information came from in terms of a region or a transmitter and will lock on or capture that site, and dispatchers can then direct their audio automatically to that transmitter site. And this is automatic steering. So we're letting the voter be intuitive and lock onto those sites. This is not often used in public safety. Dispatchers still like to control the steering of the transmitters. So let's talk about backhaul. And backhaul has been quite interesting for us in terms of manufacturers of comparators, because one of the most important means of backhauling receiver audio from my remote site is a lease line. This could be a copper line. This could be a line that's been put in place by my my service provider, my telephone company. And you look at a telephone pole, there's a lease line, a 4-wire or 2-wire lease line that allow the backhaul of information back into the voter. A T1 or TDM microwave is a good alternative, as well as RF links. So if I can't, for instance, if I have to deliver communications over a body of water, it's going to be difficult to deploy a lease line. Microwave might be too expensive. And so one of the more popular alternatives is to use an RF link, where we have UHF, parasitic transmitters and receivers delivering receive audio, in this case maybe over a body of water, and we deliver that analog information to the voter or comparator head end. And IP networks, not so much, and we'll talk about why. All right, so mixing these medias, you can have lease line, RF microwave, RF links and microwave, all backhauling into a same system. The issue we see with that is roll off. Remember, our bread and butter is spectral noise at the high end. Well, if I start rolling off information at the high end, my noise, I'm rolling off the noise as well. And I might, as a voter, look at this link and say, that's of high quality because I don't measure a lot of noise. But in fact, I'm being fooled, because the high end roll off on some of these maybe voice grade lease lines is fooling the voter. And I'm going to inadvertently vote this site when in fact the audio might not be very good, right? So we can employ equalizers, mathematical equalizers in the comparator to actually raise the noise floor up so it looks like or imitates some of the other more non-band limiting links, right? So mixing the media is not a big deal. And so we do have propagation information problems as well. And that's very important for the voter, particularly when we need to assess spectral noise all at the same time. If I have, for whatever reason, propagation delay over my lease line link, I might have termination panels, I might have distance that delivers the audio in a latent fashion. We might have other attributes that might deter communication. So I've got an example.
23 T5. Adam Young, 1955. Okay. 23, where with the Franto. I believe it was called on channel 1. Okay, we have 42 out there, but you might wait for it. Will do.
Okay, just want to add that. So you can,
482. That's 1107. Yes, sir. And the first down to Grant, my ranch there first. Okay.
all right. So you kind of get the example. So that was an example of receive audio being backhauled maybe over two different types of media, one slower, one with a little bit more delay. And if the voter doesn't vote simultaneously, you're going to get sometimes an echo effect or reverb effect. And in many cases, the loss of maybe the attack, first few syllables, or maybe words of the audio, if we don't deliver the information on time. We got ways of fixing that. So let's talk about, in my previous example there, we had lease lines, microwave backhaul, RF links, but IP, not so much. And the reason we don't like to employ a backhaul, IP backhaul, I've got a couple ROIP examples here, will be evident. But really the advantages are great. I can now offset my lease lines, which obviously have monthly recurring costs. I can maybe employ a digital network that's already at one of my radio sites that maybe the county already owns. I can maybe ride on that and leverage that network. And ROIP, radio over internet protocol, going from analog to a digital state and back to an analog state, is pretty viable, and it's a reliable technology. But there's a couple issues that we do see in terms of some of the disadvantages, and that would be jitter of the network and not latency. We can handle the latency. And the other issue, other than jitter of the network, the variation in latency, is the use of vocoders to compress the audio. We want to compress the audio such that we conserve the bandwidth of the network link, and then we deconvolute that information and deliver that to the head and voter. So let's look at a couple examples as we finish up here. And I've got an analog example. I've had 3 receivers, my transmitter, my subscriber unit in the field, quieting or somewhat quieting some of my receiver sites. I deliver the audio to the head end voter, and I have site voter modules that analyze the spectral noise, and at the same time analyze that spectral noise. And we can send that information to a transmitter. We'll vote, and we'll vote based upon spectral noise. Well, this, interestingly enough, when I deploy this analog example, I have propagation delay on one of these links. The voter is now assessing these 3 links, and the voter is going to say, hey, this is pretty quiet, when in fact the audio has not been delivered, and the voter is going to inadvertently vote this site. It'll eventually hand off to another site once that audio arrives, because it might not be that good. But that's an example of losing the attack on the transmit audio from my subscriber unit. So we can make those adjustments typically to a comparator, and we add buffering, or we store the audio at the site voter module such that we virtually realign the audio and we vote simultaneously. And the nice thing about this type of situation in terms of analog links is everything arrives, the propagation delay, once I set these delays, rarely changes in an analog type situation, lease line, microwave links, or even RF links, right? So if I take a digital example, right now I'm voting over networks. I've got ROIP devices taking analog information, compressing that information, deconvoluting that information, and reinstating the analog information at the voter head end. We can now begin voting, sending that information to a transmitter or the dispatcher. But in terms of integration, I might notice that one of my links has a little bit of propagation delay. And as you know, we can always fix that by applying buffering in to the earlier arriving audio, thus virtually realigning the audio. And I'm now treating all my receiver links equally, right? I'm not sending dead air into a site voter module, which equates to a high quality, and misvoting that site. So I can apply receive audio delay, and now I'm voting properly. So that's great. Let's say I deploy this 3 o'clock in the morning in a maintenance period, and I realign everything. I got the system voting just fine. 10 o'clock in the afternoon, noontime, when the network begins to saturate, my delays have changed because of the jitter or the latency throughout the day changes. I'll have to revisit the voter or comparator, realign the receive audio delay, realign the virtual incoming audio. And this is, again, going to change 6 o'clock in the evening when the network desaturates, the latency y changes. So I'll be chasing my tail, readjusting my receive audio delay, and that's not a good thing. And that's something most voting manufacturers do not like doing, is voting over IP networks, right? So another issue that we contend with is the degradation of audio coming from my receiver site because of the ROIP, the algorithm. So I go full spectrum into my digital link. I compress the audio using a vocoder. I deconvolute that information at the far end. And unfortunately, because of the quantization error, when we quantize the analog audio at the far end, we have to decode that information through a decoder, and there is quantization error in the analog audio. And in fact, that audio is essentially dehumanized. It's really not the original audio. To you and I as humans, it sounds like the real audio, but in fact is still been digitized and degraded. And one of the elements that gets degraded in terms of spectrum is the spectral noise. And what's important to a analog receiver voter or comparator is the spectral noise. If I artificially strip out the noise, the spectral noise, I'm unable to properly vote. So vocoders are a double-edged sword. We need those in our cell phones, our digital desktop phones. We're using a vocoder right now as we speak on this teleconference. Vocoders are a necessary evil, but for you and I as humans, we like that because the audio sounds nice and clear. But to a machine like a comparator, not so much. The bread and butter has now, which is spectral noise, has now been degraded. And so let's talk about an engineered solution for IP backhaul. So there are ways of combating that. And so let's just take a look at one of the interfaces. This is a typical analog interface that has a digital signal processor, has the ability to store audio, help assess the audio, change the gain with respect to noise. So there's a lot of things going on in this analog site receiver voter module, but it does support my receiver site through an analog backhaul link, which could be copper tie lines, RF link, or TDM microwave or a lease line. So this is still a common interface for those types of backhauls. A digital module, for instance, can now interact with the receiver sites in a different manner. So we do have a Ethernet interface on this device. This allows us to connect this information into the network. Now we're dealing with networks, and the networks can allow us to multiplex information, meaning now a single site voter module can now support multiple sites. I don't have to just support a single analog site. Now I'm leveraging the properties of a network and multiplexing on a network. And now I can place devices at the receiver site. And one of those devices can be an IP backhaul modem. And the job of the IP backhaul modem is to capture the spectral noise at the receiver site immediately, convert that information into digital information, which is lossless. Now I can compress the audio in terms of ROIP, and I already have what I want. I have the spectral noise. It's data. It's not going to change. I can impress that into the ROIP packet, deliver that to the head-end voter, and I've now circumvented the issues that I have with the quantization error of the vocoder. The other properties of a digital backhaul, an engineered solution, is that we can send information from a control element, like the control processor module in this comparator. This is a time synchronization signal that resets all the clocks in every piece of hardware in not only the chassis, but the subordinate digital site voter module will send a synchronization command to all the subordinate IP backhaul modems, essentially resetting everybody's clock, not at the same time, but creating a reference. So the beauty of a engineered system such as this is we don't rely on GPS, rubidium time sources, or timing protocols to realign the system. Remember, we want to realign the audio all at the same time. We're realigning the clocks with respect to a single system clock. So this is a fully integrated engineered system that relies on a single clock pulse. All right. So we're constantly realigning and assessing the network. And when an event occurs, such as a fully quieting of multiple receivers or partially quieting of receivers, the process begins. We capture spectral noise, we turn that into data, place that into the ROIP packet, we deliver that information back to the head-end voter. Every packet is time-stamped. The control processor module knows that. It knows how many sites are in the system, and it tells all modules in the chassis start filling their buffers. Start filling their buffers because we're going to wait for one of these sites are going to be arriving late. We're going to call that the latent site. We're going to fill our buffers until that site checks in with this timestamp. We then simultaneously dump our buffers, compare spectral noise, and realign the information. So we've combated two issues with IP backhaul. That's timing and the quantization error with respect to the vocoder. And so a lot of things are happening. We can now vote digital IP as well as analog links at the same time. So I know my time is up here. I am going to stop sharing. If you guys have any questions, I can answer. Turn my camera back on. Looks like I'm basically out of time, but if anybody